Okay, welcome back. On this time, I want to give an example of how to calculate work. But in this case, instead of being a triangular or a cylindrical tank or a conical tank that wraps itself around the x-axis, I'm going to make a triangular tank that's basically on its side. This is a good example of showing the thought process that you have to go through in order to calculate your area equation to get the whole thing set up correctly. And so with that, I'm just going to draw a tank that I'm trying to draw in 3 dimensions here. It goes down and looks like something like that. Okay, and I'm going to act like there's a spout coming off the top that has a certain distance off of it, because that distance right there contributes to the work that the liquid has to that you have to overcome to get out of the tank. So this will be the spout here. So I need to make up a dimension for this distance from the top of the spout to the top of this triangle. And this is gravity's going this way, just in case you're wondering. We're not flipping on its side or anything like that. This is the shape it's going to be in. So if we know the dimensions here, let's say this is 5 meters here. And let's just say this is 4 meters to go from here to here. And let's just make up something. We need a height. So let's just make that 5 meters as well. Okay. So, and then this distance from the spout, we'll just say that's 1 meter above the top of the tank. Okay, so this is a great problem because things aren't quite natural here. If you are drawing liquid from here, you're going to have this whole surface, and it's going to draw down this way. Okay, so it's not like you're doing your typical volume calculation. You have to stop and think about it for a little bit. So again, you ultimately want to get to where you have force here, and then you have distance along this side. Because we're dealing with liquid and pumping and overcoming gravity, I like to always say that the spout is the origin. So the spout would be right here, and then not until really 1 meter is the mass of the liquid starting to come out. And then it goes all the way from 1 meter to 6 meters here. So, but first, we have to set up the equation properly. And it's really the shape of the tank as a function of x. That leads to your area as a function of x, which leads to volume as a function of x. And then it goes to mass, and then force, which gets you right to work. Okay? So these two are really easy because that is really just density, and that is just really a multiplier of the acceleration of gravity. So we can go right from volume to work relatively easily. But first, we have to figure out how do we define the shape, and how does that get us to the area? Well, if we turn everything on the side, and we have our x-axis and our y-axis here. And we'll say the spout is here at the origin. And we'll say gravity is this way. Or actually, it's actually pulling this way. G, gravity. Okay, well then we have essentially this first face here, which is a big rectangle, and that goes down to a point. Okay, and this starts at x equals 1 and ends at x equals 6. Okay, so we just need to figure out now. We can go, because this is a weird shape, I think we want to go directly to what is your area as a function of x. So we know that the height of this is 4 meters. I'm going to say area as a function of x. Okay, so my area, it's always going to be a rectangle, right? So it's always going to be length, or I'll just call it base times height. Base times height, okay? And so my height is always going to be equal to 4, okay? 4 meters. Area x. So what is my base going to be equal to? Well, they told us at this particular point it's equal to 5. So at x equals 1, then our base equals 5. At x equals 6, the base equals 0. Okay, so this is actually going to manifest itself. We can actually extrapolate it backwards one. So we can say at x equals 0, well, it's going to be a little bit greater than 5. It's actually going to be base equals to 6. As I can see, it's decreasing 1, because this is a distance really of 5 here. And this is decreasing at a rate of 1 per unit of x. So don't believe me, just give it a try and think about it. So now I've got, and it doesn't matter, my tank doesn't really, at this point, have to start and stop at 1. It can keep going. And I'm going to control where it starts and stops when I do the integral for volume, because I'm just going to go between it. I'm going to act like A is 1 and B is 6. So thinking ahead a little bit, I can kind of say, what is my base as a function of x? So it's going to be 6 minus x. Right? So when x is 0, I'm going to get 6. When x is 1, I'm going to get 5. And when x is 6, I'm going to get 0. So my a of x, I'm just going to distribute this out, is 24 minus 4x. Hopefully that makes sense to you. So that is going to be that area of that front face, this face here, as you change x. And it doesn't matter, I don't have to program in the start and stop points. That's all taken care of with this calculation right here. And I don't really have to worry about this part above the tank, because I'm going to calculate that out later. So knowing this, area x, if you remember, volume equals the integral from b to a of x dx. Okay, so next board. Okay, so where we are now is we have a function for area in terms of x. For x, we have volume now. I'll just say per x. It's going to be from b to a, area x dx. So we know what the area is here. Work now equals force times distance. Okay? Which means we have to convert this volume into a force, which is just taking that volume, the density of water, which is 1,000 kilograms per meter squared, and then gravity is 9.8 meters per second squared, and multiplying those together times the area. So what we're going to have is the integral from B to A, the density times gravity times area as a function of x, and then I'm going to leave a spot right here for where our distance is going to plug in, and then we're going to have dx. So all of these things together equal your force. So the density, gravity, area, and times that change in x. So now if you remember, we have our little triangle shape here, and this is along the x-axis. We have the y-axis here. So from the origin to the start of our tank, right there, so is the distance. Once we have the distance here, so as our x goes along here, we can just put in an x there, and then that takes care of that distance. There's nothing fancy about it. So it unfortunately complicates things in a little bit, but that's just the way it is. You're just going to be left with what you're left with. Alright, so that's the distance. The force is the rest of it. And now let's plug some numbers in. So work equals, I'm going to take the density and put it on the other side of the integral because it doesn't really matter. It doesn't do anything if it's on the other side. Square. And then I'm going to say times gravity because it's also a constant. Okay. And now the integral. So we are going from 6 is out here, and we're going to 1 is right here. Now, so that'll take care of where the water level is. So then we have 24 minus 4x times x dx. Okay, everything's taken care of. Come down to the next line. 800. The integral 6 to 1. We have now distributing that x into the parentheses. Gives us that there. Again, this is work. Work equals 9,800 times the quantity. I'm just going to do the integration right here. I'm going to leave it at that. And so I'm going to have 24 divided by 2x squared. And then I'm going to have minus 4 divided by 3x cubed. And that's going to be from 6 to 1. Okay, so the next step is just plugging in 6 into x, and then subtracting out the plugging in 1 into x, and we'll get our answer. So hopefully that helped. Everything is in the setup. There's a couple different ways to do it, and so I'm going to do a few more videos. So subscribe to the channel, and you'll be able to see when the new posts come out. So anyway, hope this helps. Talk to you later.